It's time to experience something glorious. Unacademy Combat. Compete, crack, conquer.
A challenging GATE contest engineered to give you an experience like none other.
Where you put your knowledge to test
and battle it out with a test.
To bring out the best in you, Unacademy Combat is the most competitive, gamified contest for GATE till date, with the best of the questions by best educators.
with detailed video solutions from top educators right after each contest.
Combat live with peers to get real-time rankings and win big.
Participate in every contest to improve your ratings.
Challenging contests every fortnight or alternate Sunday. Live ranking after every question. Big rewards for top rankers. Your passion to crack GATE deserves this. Your hard work towards your dream deserves this. Fuel your inner fire for the ultimate GATE challenge. Unacademy Combat. Register now.
Hi, hello, good evening all. Welcome to Unacademy. Good evening. Bharat, good evening. Good evening, Ramakrishna. Good evening all. Okay. So for new joinings, let me introduce myself. My name is Banu Prakash, expert in GATE and ESE coaching. I did MTech from NIT Kurukshetra. I have 10 plus years of teaching experience and I train many students throughout our country for different competitive exams like GATE, ESE and many PSUs. Expertise in the subjects of electrical machines and power electronics. BPC 10 is my referral code. Use this code, you will get 10% to discount on the Plus subscription as well as iconic subscriptions. Got it? Abhiram, good evening. Hi. And what are the benefits of the Plus and iconic subscription? By taking Plus subscription, you can get live classes from the top educators of the country. So here you have a choice to select the teacher, for each subject, so that you can select the teacher as per your choice. There are many number of the teachers in for each subject. So next one, you can get structural schedule, unlimited practice questions, and fourth one is a test series. So by writing the test series on every weekend, so you can analyze your performance, whether you are fit for the competitive exams or not. And other one, whenever you are lagging, so then you can improve your performance by knowing the test results. Okay. And another subscription is a iconic subscription. So this iconic subscription, by taking iconic subscription, you can get all 4 benefits. In addition to these, some extra benefits. One is a personal coach, study planners, expert guidance, ESC mains, questions and answers. Personal coach means he will guide, that is a one-to-one guidance for your GATE and ESC preparation. Okay, he will guide everything until you crack your exam. And second one is a study planners. So you can get proper study planners, how to crack GATE or how to crack any PSUs or how to crack AE exams, many more exams like. And also you can get expert guidance, ESC mains, questions and answers. So this is the iconic subscription, is a complete package. Okay, you can get more benefits by taking iconic subscription. So if you want to take the subscription, so use my code BPC10 is my referral code. This is you will get, by using this code, you will get 10% to discount on Plus subscription as well as iconic subscriptions. Okay. And another one is a what about the price for the Plus and iconic subscription? The Plus subscription is available for 12 months, 18 months and 24 months. For 12 months, fee is 27,225 rupees. Okay, for 18 months, fee is 34,650 rupees. Okay, for 24 months, fee is 39,600 rupees. Okay, iconic subscription is available for 12 months and 24 months. For 12 months, 125 rupees. For 24 months, fee is 66,600 rupees. And there is a question, how to install Unacademy learning app in your phone. So just do one thing, okay, search Unacademy learning app in your phone, and after that install this app and access the pre-special classes taken by the top educators. So if any code is asking, then use my code BPC10. So it is an invitation code for Unacademy's pre-special classes, and also it is a referral code to get the 10% to discount if you take the subscription. Okay, you can use both. One is a invitation code for the pre-special classes, and second one is that is by using this code you will get 10% to discount on Plus subscription and as well as iconic subscription. So this is the January month schedule of Unacademy GATE English channel. So this is our channel. All of you share this channel and subscribe, like and share to this channel to your friends. So this is the month of January month schedule. Communication system 9 to 10 a.m. Engineering mathematics 10 to 11 a.m. Analog electronics 4 to 5 p.m. and foundation course for maths, foundation course on mathematics for GATE 2022-23 5 to 6 p.m. and another one foundation course on aptitude for 2022-23 at 6:15 p.m. to 7:15 p.m. So next one, this is the measurement class 7:30 p.m. to 8:30 p.m. and your electrical machine 8:30 p.m. to 9:30 p.m. Okay, Abhiram, I will apply. I will update this part. Lecture number 2 today. Any more question do you want to ask? Okay, good evening, Revati. Good evening. Okay, listen. In previous class, we had discussed about operating principle of the transformer and working of the transformer. So, transformer operates on the principle of Faraday's laws of electromagnetic induction. It states that an EMF induced in a transformer winding is directly proportional to rate of change of flux linkage. And how does EMF induce? Okay, so that part already we have discussed. Initially, whenever transformer is excited with the AC supply, time varying nature of the current passes through the winding. As a result, MMF set up initially in the winding and thereby flux will be created. So this flux the also links, flux produced in the primary winding also links in the secondary winding through the transformer core. So according to the Faraday's laws of electromagnetic induction, EMF induced in the primary winding as well as secondary winding of transformer. So this part we had discussed in the previous session. So today we will discuss about that is a EMF equation of the transformer. How to derive the EMF equation of transformer. So we know that transformer has two major parts. One is a transformer core and second one is transformer winding. So transformer windings are two types of one is the HV winding and LV winding. So one winding is connected to the supply. Suppose this winding is connected to the supply. This is a single phase AC supply. So the winding which is connected to the supply is known as a primary winding of transformers. We had discussed this part and it has N1 number of the turns. Okay, similarly, and the winding, other winding of the transformer, other winding which is placed on the same core is known as a secondary winding of transformer. So this secondary winding has number of turns, N2 number of the turns. So what will happen exactly when transformer is excited with the AC supply? So this AC supply is a V of T, okay, time varying nature of the supply voltage. So now time varying nature of the current passes through, okay, this is the I nu of T here. Time varying nature of the current passes through the winding. Just imagine the current enters at, for example, so we have this is the limb of the core. So just this is the limb of the core here. So in this case, winding placed on the limb, okay, as shown in the figure like this. So it is excited with the AC supply, right? So therefore what will happen? Current passes through the winding. So just imagine this is the current entering position and this one is the current leaving position. According to right hand thumb rule, so how do we obtain the direction of the flux? This direction of the flux can be obtained by using the right hand thumb rule. So according to the right hand thumb rule, if the orientation of the fingers around the conductor, around the core indicates the current direction, then thumb indicates the flux direction. Suppose here current entering, like, okay, this is the current direction. So what will happen? The flux around this conductor, okay, flux is a, so this is the direction of the flux, okay. So here flux direction, flux in the core, okay, this one is the direction of the flux. So that's why flux produced in the primary winding pi 1. So this flux links in the secondary winding through transformer core, okay, this is the transformer core. So now what will happen? According to Faraday's laws of electromagnetic induction, the EMF induces in the primary winding as well as EMF induces in the secondary winding of transformers. Okay. So this is the complete discussion about how does EMF induced in the transformer windings. All of you got it, my point? So whenever transformer is excited with the AC supply, time varying nature of the current passes through the winding. As a result, the flux is as a result MMF set of initial, and thereby flux will be created. So according to the Faraday's laws of electromagnetic induction, EMF induced in the primary winding as well as EMF induced in the secondary winding of the transformer. So but our question is, how do we derive this EMF equation and EMF equation of the transformers? Okay. Is that clear, everyone? Yes or no? Okay, let assume, let N1 is primary number of turns in the primary winding, turns in primary winding, okay, where N2 is number of turns in secondary winding of transformers, okay. And V of T, okay, V1 of T is the source voltage or supply voltage, time varying nature of the supply voltage of the transformer, or the voltage where this is the voltage excited, the transformer is excited with the supply voltage of V of T. And next one, I nu of T. Okay, what is the meaning of this? It is a magnetizing current of the transformer. So how do we define this magnetizing current? So magnetizing current means the current required from the source to create flux in the core, or the current required from the source to create the flux in the transformer core is called magnetizing current. Okay, so therefore how do we define this? The current required from source to create flux in transformer is known as magnetizing current. So remaining another one, V1 of T. So what is the meaning of V1 of T here? So this is the instantaneous induced EMF. Instantaneous induced EMF in primary winding of the transformer. So what is the meaning of instantaneous? That is it depends on the position or instant, okay, instant of the time. So that's why it is known as the instantaneous induced EMF in the primary winding. Now similarly, V2 of T also. So this is the instantaneous induced EMF in secondary winding of transformer. So these are the terminology used to derive the EMF equation of the transformer. N1, N2, V1, I2, E1 and E2 values. So we know that the transformer is a pure inductive natures. Got it point? So we know transformer is pure inductive nature. Okay, so magnetizing current lags applied voltage V1 by 90 degrees. Got it point? Suppose if applied voltage, if V1 of t is equal to the Vm sine omega t, okay, sine omega t. So then the magnetizing current, instantaneous magnetizing current I nu of t is equal to, okay, this I nu of t. So what will happen? So this t is equal to I maximum the sine omega t minus the 5 by 2 here. Okay, so all of it clear point. We know transformer is a pure inductive nature, so magnetizing current always lags the applied voltage by 90 degrees. So if V1 of t is equal to Vm sine omega t, then I nu of t is equal to Im sine omega t values here. Suppose if this is if applied voltage, the V1 of t is equal to Vm maximum value the sine omega t plus 5 by 2. So then what will happen? The I nu of t we can write, so that is equal to I maximum the sine omega t. So let us assume this is the equation 1. So we can take any one. So either first equation or this one. So here in this case this one is the reference. Okay, here when if V1 of t is equal to Vm sine omega t plus 5 by 2, then magnetizing current lags the applied voltage by 90 degrees. Okay, all of it clear now? So after that, how do we get the flux here? So we know here flux in the primary winding. Okay, so now here flux in the primary winding, flux in primary winding of the transformer. So it is denoted by phi1 of t is equal to, okay, phi1 of t. So it is a MMF divided by the reluctancy of the core. So what is the MMF in the primary winding? So now it is equal to number of turns in the primary winding, so into magnetizing component of the current divided by reluctancy of the core. So now simplify this. Okay, it is equal to the N1, okay, Im the sine omega t divided by the reluctancy of the core. So therefore the phi 1 of t is equal to, so N1 phi I maximum divided by the reluctancy of the core, the sine omega t. Okay, this sine omega t. So from here we can write phi 1 of t is equal to some maximum value of the flux sine omega t. So let us assume this is the equation 2 here. So just see these two equations. I nu is equal to Im sine omega t. Okay, and similarly flux is equal to phi maximum sine omega t. So from 1 and 2 equations, so what we conclude in the transformer? Tell me, from 1 and 2 equations, what we will conclude? Same pace, very good. Okay, that from 1 and 2 equations, what we conclude? The magnetizing current and flux of the transformers are in phase with each other. Very good. Okay, so next one, let us find out EMF induced in the instantaneous induced EMF in primary winding of the transformer. Okay, so that is denoted by V1 of T is equal to minus N1, the differentiation of the flux with respect to that time. So now simplify here, the minus N1, so differentiation of the flux. Flux is equal to phi maximum sine omega t with respect to that time. So now simplify this, okay, minus N1 maximum value of the flux, omega, okay, cos omega t. Okay, am I right? So now this equation we can written as minus N1 phi maximum omega the sine pi by 2 minus, okay, omega t. Okay, so now again this is a minus sign is a common, so this equation N1 phi maximum omega the sine omega t minus, okay, pi by 2 1. So this is a, let us assume, equation 3 here. Okay, equation 3. So now what about this value? Okay, here otherwise I will write. So what about this one, N1 phi maximum omega? So here we can write, so V1 of T is equal to, so that is the V1 maximum, so that sine omega t minus phi by 2. Okay, so where this is a V1 maximum is equal to, okay, V1 maximum, so that is a N1 phi maximum omega values. So let us assume this is the equation 3. Okay, equation 3. Why this here, why it is called as instantaneous induced EMF? So it depends on the position of the omega t here. So when omega t is equal to 0, okay, this is the some value. So always that depends on, for example, if the flux is a here, so this is a, so flux in this case, okay, it is a phi 1, the flux, the omega t, it depends on the omega t. Got it, mind? So what will happen in the induced EMF? So after 90 degrees time delay, the EMF induces in the transformers. Okay, EMF induced. So now this is the primary induced EMF. So here, so what about the phase displacement? Okay, this is the pi by 2. Okay, so at omega t is equal to pi by 2. So what is the EMF induced in the transformer here? 0. So at omega t is equal to phi, it has a maximum value. So at omega t is equal to, okay, 3 by pi by 2, then you will get that 0. And it is a maximum negative values. So it depends on the position or instant of the omega t. That's why it is treated as a instantaneous induced EMF in the primary winding of the transformer. Is that clear now? Okay, very good. Any more question do you want to ask? You can ask. Any type of question you can ask. I am here to explain all type of the questions. Okay. So now we have a question. So all AC voltages measured in the RMS value. So this is the AC nature of the induced EMF. So that how do we measure? Okay, this value, all AC voltages or AC currents are measured in the RMS value. So let us find out RMS value of induced EMF in primary winding of the transformer. Okay, primary winding of transformer. So this is a V1 RMS value. So it is denoted by capital E1. Okay, so how do we get RMS value? Always maximum value divided by root 2. Okay, this is the RMS value divided by the root 2. So therefore E1 is equal to, so E1 maximum is a N1 phi maximum, okay, omega divided by, okay, under root. Okay, clear my point? So from here we can write E1 is equal to N1 phi maximum, omega is a 2 phi F, okay, divided by under root. So now simplify this. So by simplification, E1 is equal to 4.44 phi maximum Fn1. Okay, Fn1. So got it point? So this is the phi maximum Fn1. So this is a EMF equation of the transformer in primary winding. EMF equation of transformer in primary winding. All of you clear my point? Okay. So next one, similarly, instantaneous induced EMF in secondary winding of the transformer. Okay, so this is the denoted by V2 of T is equal to minus N2, okay, d phi 1 of T with respect to the time, differentiation of the flux with respect to the time. So let us substitute this flux here. E2 of T is equal to the minus N2, the differentiation of the flux phi maximum sine omega T, okay, with respect to the time. So now simplify this equation. The V2 of T is equal to minus N2 phi maximum omega, that is a cos omega T. So now let us write this equation in terms of the sign. So V2 of T is equal to, okay, so N2 phi maximum omega, the sine omega, yes, sine omega T minus pi by 2. So where E2 of T is equal to, so this is a E2 maximum, right? The E2 maximum, the sine omega T minus pi by 2 1. So let us assume this is the equation 4. Okay, so here flux is also, okay, where in this case, so where E2 maximum is equal to, where this is the E2 maximum, so that is equal to N2 phi maximum omega. So in the equations point of view, suppose that let us write instantaneous induced EMF. So this is the omega T, and here suppose flux is a phi is equal to, it is a phi m sine omega T. It is also sine function, that is a E2 maximum, okay, omega T. So after 90 degrees time delay, the EMF induces in the secondary winding of the transformers. Okay, EMF induce. So this is the flux produced in the primary winding phi 1, and this one is the EMF induced in the secondary. So phi 1 of the t depends on the time. Okay, phi 1 of the t. So where omega is a angular frequency, right? Got it my point? So E2 maximum is equal to N2 phi maximum omega. But we required EMF equation. Then how do we derive this EMF equation? All AC voltages measured in the RMS value. So therefore RMS value of induced EMF in secondary winding of transformer. Okay, got it? So this E2 maximum, this way, it is represented with E2 RMS value. It is denoted by E2. So therefore capital E2, so it is equal to E2 maximum divided by under root, right? So now this value is equal to N2 phi maximum omega divided by root 2 here. So where omega we can write, so this is the N2 phi maximum omega is a 2 phi f, so divided by the root 2 values. Now simplify this. So here by simplification, therefore you can get E2 is equal to 4.44, okay, phi maximum omega phi maximum f N2. Okay, this is a EMF equation in the secondary winding of the transformers. Okay, so for example point, so we have a ratings like single phase, the 50 hertz, the 400 upon 200 volts, the transformer. Okay, we have seen some rating on the nameplate details of the transformer. So these two values are, so here always, okay, it is a the V1 are here V1 by E2 only. Okay, these are the RMS values. Okay, so it is not a maximum. So V1 in the sense here the V1 RMS value EMF induced in the primary winding, and this is the V2 in the sense E2 RMS value. RMS. So that what we conclude, the voltage rating is mentioned by the manufacturer on the nameplate details of the transformer that represents RMS induced EMF. It is always primary induced EMF to the secondary induced EMF. Okay. Is that clear, everyone? Okay, so what are the conclusions I can make from this discussion? So conclusions. Okay, so first conclusion is the first one is, so magnetizing current, okay, lags the applied voltage, okay, applied voltage by 90 degrees in transformers. What is the reason? So here is a transformer is a pure inductive nature, so that magnetizing current lags the applied voltage by 90 degrees. Okay, this is the one conclusion. And second one is, okay, magnetizing current primary flux of the transformer phi 1 are in phase with each other. In phase with each other. Okay, this is the second conclusion. And third one is what about the primary induced EMF? So E1, okay, lags the phi 1 by 90 degrees, right? Lags the 90 degrees. Okay, similarly, fourth one is the E2 also lags phi 1 by 90 degrees. So that what we conclude, E1 and E2 are in phase with each other. So this is the in transformer, primary induced EMF and secondary induced EMF are in phase with each other. So next one, here how do we draw? Suppose if I take the flux, first one, applied voltage, okay, V, I have taken applied voltage. So this is the V here, and magnetizing current always, okay, it is the V1. So magnetizing current lags the applied voltage by 90 degrees. Got it? So now flux and magnetizing current are in phase with each other. So let us assume this is the flux is the reference one. So here is a magnetizing current and flux are in phase with each other. So applied voltage leads the magnetizing current by 90 degrees. So that's why we have written as V1 of t is equal to, so V maximum the sine omega t plus pi by 2. Okay. So now how do we written this one? Okay, it is equal to I maximum the sine omega t, right? So next one, this induced EMF, so E1, okay, lags the flux pi 1 by 90 degrees. Now similarly E2 also the lags the flux pi 1 by 90 degrees. So this E1 is the E maximum the sine the omega t minus pi by 2. Okay, E2 maximum. So E1 maximum. So now this is also E2 maximum the sine omega t minus pi by 2. So like this you can conclude all the conclusions. Okay, magnetizing current lags the applied voltage by 90 degrees. Magnetizing current and flux of the transformers are in phase with each other, and EMF induced in the primary winding lags the flux by 90 degrees. And the fourth one is EMF induced in the secondary winding lags the flux by 90 degrees. Okay. Okay, all of you clear about these conclusions? Any more question do you want to ask? You can ask. Okay. So now let us discuss about what are the observations from EMF equation of the transformer. Okay, so observations are very important for competitive exams, just like all possible questions from the EMF equation of the transformer. So we know the EMF equation. So we know that EMF induced in the primary winding E1 is equal to 4.44 phi maximum Fn1, right? EMF induced in the secondary winding, so that is equal to 4.44 phi maximum Fn2. Okay, this is the EMF equation of the transformer. So sometimes we have a question, the question number 1 from the EMF equation. Okay, what is the question? See, so EMF equation of the transformer in terms of the flux density and net cross sectional area of the transformer core. So this is the EMF equation of the transformer in terms of maximum flux density and net cross sectional area of transformer core. Okay, so this AN in the sense, okay, net cross sectional area, cross sectional area. So that means area occupied by magnetic material only. Okay, that is known as a net cross-sectional area. Or area occupied by both magnetic material and insulating material is known as the gross cross-sectional area of the transformer core. So where this one is a flux density of the core. Okay, it is a flux density of maximum flux density of the transformer core. So we have a question, EMF equation of the transformer in terms of the flux density and net cross area of the transformer core. So this one is a sometimes B maximum and here number of turns, frequency are given in the transformer in the data and asking about the net cross sectional area. Sometimes net cross sectional area remaining parameters are given in the given, and then they will ask the question based on the maximum flux density of the transformer core. So how do we calculate? So we know that here we know. So here is a E1 is equal to, okay, this is the E1 is equal to 4.44. So 5 maximum Fn1. Similarly E2 also equal to 4.44, 5 maximum Fn2. So let us assume this is the equation 1. So we know, okay, here the maximum flux density of the core is equal to the maximum flux divided by net cross sectional area of the core. So from here maximum flux is equal to B maximum net cross sectional area of the core. So now this is the equation 2. So now substitute the equation 2. Okay, substitute the equation 2 in the equation 1. So we get, okay, this is a, so here E1 is equal to 4.44 B maximum AN Fn1. Similarly E2 is equal to 4.44 B maximum AN Fn2. So this is the EMF equation of the transformer in terms of the flux density and net cross sectional area of the transformer core. So any the 4 parameters, for example 1, 2, 3, 4, 5 is there. The are any 4 the parameters are mentioned in the question and asking about the 5th one. Sometimes all this with some question about the B maximum, question about the net cross sectional area. Or all are given, find out the induced EMF. Or all are mentioned, find out the number of the turns. So these are the all possibility question based on the this EMF equation. Okay, is that clear everyone? And similarly one more possibility of the question from the EMF equation. The second one is a EMF per turns ratio of EMF per turns ratio of the transformers. Okay, so what is the EMF per turns ratio of the transformer? This also can be obtained by using the EMF equation of the transformer. So from the above observations, okay, from observation 1, okay, observation 1, so we get, so that is a EMF induced in the primary winding. So E1 is equal to 4.44, the B maximum AN Fn1. So here E1 divided by N1 is equal to 4.44 B maximum AN, okay, ANF. So similarly the E2 is equal to, similarly here the E2 is equal to 4.44 B maximum AN Fn2. So now find out the ratio of induced EMF to the number of turns. E2 by N2 is equal to 4.44. So B maximum ANF. Okay, got it, fine. So from here we can conclude that EMF induced, EMF per turns ratio in the primary winding is equal to EMF per turns ratio in the secondary winding. So that is equal to the 4.44 the B maximum ANF. Okay, ANF values here. So this is the EMF per turns ratio in primary winding of the transformer and secondary winding of the transformer. All of you got it? So from this equation, what we conclude here, the EMF per turns ratio, okay, EMF per turns ratio in primary winding is equal to the EMF per turns ratio in secondary winding of the transformers. Okay, so always EMF per turns ratio is a constant from the primary winding to the secondary winding of transformers. So this is the second possibility question from the EMF equation of the transformers. Okay, all of you clear my point? And another possibility of the question from the EMF equation of the transformer, so that is a third one. So it is a transformation ratio of the transformer. Transformation ratio of transformer. Okay, so it is denoted by capital K. Okay, this is the always the transformation ratio is the capital K here. So from the above observations, okay, see here, so from observation 2, so we get that is a N2, either E1 by N1 is equal to E2 by N2, that is equal to 4.44 B maximum ANF. Okay, got it mind? So this is the sum E1 by N1. So let us assume this is the sum constant value. So E1 by N1 is equal to E2 by N2. So this one is so we can written as E1 by N1 is equal to E2 by N2. Okay, this is the same. So let us rewrite these terms. Okay, that is a N2 by N1 is equal to, so E2 by E1. Okay, E2 by. So this is a ratio from the secondary number of the turns to the primary number of the turns. So that is denoted by the transformation ratio K. Okay, so this is the transformation ratio. Suppose we have a question, sometimes what about the here turns ratio of, okay, note the turns ratio. How do we get turns ratio here? The turns ratio denoted by the small a. So this is always reciprocal of the transformation ratio. So that is equal to N1 by N2. Okay, it's the turns ratio of the transformer. So always reciprocal of the transformation ratio, N1 by N2. Suppose we have a example point. So there is the data like this, the single phase 50 Hz, okay, 400 upon, okay, 200 volts transformer. Okay, so how do we get transformation ratio from here? Okay, this is always, I already mentioned that. So this voltage rating mentioned on the nameplate details of the transformer. So this is always E1 by E2 only. Okay, E1 by E2 only. So therefore transformation ratio, okay, transformation, the ratio of transformer, so that is the K is equal to, so how do we get, that is N2 by here, E2 by E1, so it is equal to 200 divided by the 400, it is equal to 0.5. So next one, turns ratio is equal to, so how do we get turns ratio? So this turns ratio, the A is equal to 1 by reciprocal of the transformation ratio. So it is a 1 by 0.5. So it is equal to 2. Okay, like this you can answer this question. So any voltage rating mentioned on the nameplate details of the transformer. So that is the always E1 by E2 only. Very, very important for the problem solving in case of the transformer. And what about the turns ratio? Turns ratio is a reciprocal of the transformation ratio. Okay. Very good. Okay. Any more question do you want to ask? Okay, so next one, there is another possibility of the question from the EMF equation. Fourth one, that is a relation between size of the transformer and frequency of the transformer. So what is the relation between the size of the transformer and frequency of the transformer? So I have asked this question in the first class. How do we obtain the relation between size of the transformer and frequency of the transformer? So it can be obtained by using the EMF equation of the transformers. Anyone can answer this relation? Okay, listen. So we know EMF, the EMF per turns ratio in the primary winding, E1 by N1 is equal to EMF per turns ratio in the secondary winding, that is a E2 by N2. So it is equal to 4.44. Okay, B maximum, okay, B maximum ANF. So this is our relation. So here suppose B maximum is some finite value. Okay, this is the finite value. Suppose it is a 1.6 for the silicon steel material. Silicon the steel, okay, material. For example point I have taken. So maximum value B maximum is some finite value 1.6 for the silicon, or this is 0.6, 1.6 for the silicon steel material. You can take any finite value. So example point I have taken. So this is the example point 1.6 for the silicon steel. So here if the supply, for example, if the size of the transformer, if the size of the transformer increases, okay, increases, so then operating frequency of the transformer should be decreased. Okay, operating frequency of the transformer should be decreased in order to maintain, so this EMF per turns ratio constant. Okay, I repeat once again. So as the size of the transformer increases, operating frequency of the transformer will be decreased in order to maintain the EMF per turns ratio constant. So due to which what we conclude, the size of the net cross-sectional area inversely proportional to frequency of the transformers. Got it? So here as size of the as here net cross-sectional area AN is increased during the designing of the transformer operating frequency okay will be decreased, right? Decreased to maintain EMF per turns ratio constant. Okay, so therefore, so here the AN inversely proportional to the frequency of the transformers, right? So from this equation we conclude that the size of the transformer, okay, inversely proportional to the frequency of the transformer. frequency of transformers. Okay, got it? Size of the transformer is inversely proportional to frequency of the transformer. So this is our relation. All of you got it? So that's why transformers which are used in the electronic device are less in size as compared to transformers which are in the electrical power system. What is the reason? Electrical frequency is a 50 Hz frequency and electronic frequency is a kilohertz frequency. So that here in order to operate the transformer for kilohertz, the size of the transformer should be low as compared to electrical transformers. Okay, and one more conclusion also there. The Indian operating frequency is a 50 Hz and USA operating frequency is a 60 Hz. So that's why the USA made transformer is a less in size as compared to India made transformers. Okay, so these are the conclusions here. Okay, all of it clear? Is that clear or not? Please respond, then we will discuss very effectively. If you have any question, you can ask. Very good. Any more doubts? Do you have any question or any doubt? You can ask any type of the question. Okay, don't feel shy to ask any question, whether it is easy or difficult. I am here to explain. We can increase, but our system actually the operating frequency that is depends upon the generating side. So we have to increase the complete size of the turbine, size of the dam. That is a difficult. So that always electrical frequency the 50 Hz. So F is equal to we know that F is equal to operating frequency Pn by 120, right? So in electrical power system, in generating station, so generating system, okay, here frequency power is generated, the number of the poles, and this is the speed here, right? So in our here we have to increase the number of the poles, we have to increase the speed here. So to increase the speed, we have to increase the size of the turbine. So as the size increases, then what about cost here? The cost of the electrical power will be increased, which is not desirable. So that is the one. Already we have set a system with a frequency of the 50 Hz only. Yes, I will tell you that part. Next question is a very good. So fifth one is a relation between KVA rating of transformer and frequency of the transformer. Okay, so KVA rating means always the transformer rating mentioned in the apparent power instead of the active power. What is the reason? So rating of any electrical machine that depends on the temperature rise. Okay, suppose for example here the power is equal to power output in the watts or in kilowatts, that is the V2 I2 the cos theta 2, right? So here this is a iron loss depends on, okay, this the rating here, the iron loss that depends on the voltage rating, and whereas the copper loss depends on majorly the this is a current I2, right? So voltage measured in the, okay, in volts. Okay, next one, current in the amps. Okay, we know this part. So but what about this power factor? It is nothing but it is a load power factor, right? So this load power factor, so here load power factor, okay, load power factor, that is the cos theta 2. So during the designing, the manufacturer doesn't know about the load power factor. So whether it is connected to 0.6 power factor, 0.8 power factor, 0.2 power factor, or 0.9 power factor, or unity power factors, so that he was considered as highest power factor of the load. So if power factor, what is the highest power factor of the load here? So if power factor is equal to, okay, if the load power factor is equal to 1. So 1 in the means highest power factor, okay, highest power factor of the load. So okay, he was considered as highest power factor of the load. So if the load power factor is equal to 1, so then what will happen? So this active power, so active power will become, okay, so apparent power. Okay, got it point? So when apparent power means, that is the what? Okay, here is a V2 multiplied by I2. So this up, that's why here KVA rating of the transformer, KVA rating, okay, KVA rating, here this rating, power rating of the transformer, power rating of transformer is measured in the KVA instead of the kilowatts, right? So this is the reason behind this one. So KVA, here is a power rating of the transformer is measured in the KVA instead of the kilowatts. What is the reason? The rating of any electrical machine, okay, designed based on the temperature rise. So temperature rise means that is a losses. How much amount of loss comes from the transformer? So majorly what are the losses in the transformer? One is the iron losses and copper losses. So iron loss depends on the voltage which is measured in the volts, whereas copper losses measured in depends on the current which measured in the amps. So what about this power factor? So this power factor, so manufacturer doesn't know about the load power factor, so that he was considered as highest power factor of the load. So if the load power factor is equal to 1, so this active power will become apparent power, so that it is measured in the KVA instead of the kilowatts. Okay. So then what about the relation? So we have a question about, this question is a required. This is the only discussion. So why transformer rating mentioned in the KVA instead of the kilowatts? But what is the question? Relation between the KVA rating of transformer and frequency of the transformer. So how do we answer this question? So power rating of the transformer, okay, power rating of transformer, so that is a, so it is equal to volt amperes or kilovolt, right? Kilovolt amperes or megavolt amperes. Okay, so depends upon the size, volt amperes, kilovolt amperes and megavolt amperes. So therefore you can write the KVA rating of transformer is equal to KVA rating of transformer. So that is equal to E1 multiplied by I1, voltage rating multiplied by the current rating. So that in the primary side, it is also V2 multiplied by I2. So we know that transformer is a constant power device. Power is same in the primary winding and secondary winding. So from these equations, what we conclude, the here voltage rating or kVA rating of the transformer, kVA rating of transformer, the directly proportional to the induced EMF E2. Okay, got it point? So from this equation you can write directly proportional to the induced EMF. So this is the, let us assume equation 1. So we know induced EMF is equal to the year. So this is the at E2 is equal to, so 4 point, okay, this is the 4.44 pi maximum F N2, right? So at the constant flux and number of turns are constant. So therefore E2 directly proportional to the frequency. So let us assume this is the equation 2. So from the equations 1 and 2, so we get the kVA rating of the transformer. Okay, kVA rating, okay, directly proportional to the frequency of, okay, frequency of the transformers. So here size of the transformer is inversely proportional to the frequency. So whereas kVA rating of the transformer is directly proportional to frequency of the transformers. All of you got it, my point? So this is the power rating. The power is directly proportional to the frequency. kVA rating is a power rating of the kVA rating of transformer directly proportional to the frequency. Whereas size of the transformer is inversely proportional to the frequency. Now, any more question here? Okay, what is the relation between the size and kVA rating of the transformer with frequency? Okay, so next another possibility of the question from the EMF equation. So that is the sixth one. Relation between, okay, relation between maximum flux density of the transformer core and V1 by F ratio of transformer. Okay, this is also very important to solve the many questions in the transformer part. For any transformer, your Indian electrical frequency is a 50 Hz. Okay, if it is a transformer which is used in the electronic device, is not a 50 Hz. The electronic frequency the only kilohertz. So that's why the transformer which is used in the electronic device is less in size as compared to electrical the transformers. If it is increases, suppose if the frequency is, you can design the transformer, suppose with a high rating of the frequency also, but that is a complete, our grid, electrical power grid is a designed at a frequency of the 50 Hz. So that we have to design the transformer to operate at the 50 Hz only. Okay, see here, here the kVA rating in the means that is a temperature rise, temperature of the transformer. The temperature in the means that is the losses, right? Okay, what are the losses in the transformer? So one is the iron loss and also copper losses of the transformer. So this iron loss depends on the voltage rating, and whereas the copper loss means I square R losses. Okay, I square R losses in the winding. Iron losses means applied voltage multiplied by iron loss component of the current. So here iron loss depends on the voltage rating, whereas copper loss depends on the current rating. So voltage rating means that it measured in the volts and amps. But what about this power factor here? So cos theta 2, it is a load power factor. Suppose manufacturer doesn't know about this load power factor. Suppose here there is a transformer. So here if this transformer here load is connected. So we don't know what is the load power factor, whether it is a inductive load, capacitive load, or whether it is a resistive load. So that's why he was considered as, manufacturer considered as a highest power factor of the load. So that you can operate any power, any power factor. If it is a 0.1, so we cannot operate more than the 0.1. So that's why we have the design with the load power factor is equal to 1. So if the load power factor is equal to 1, then active power will become apparent power. Okay, Revati. Have we got it now? Why kVA rate? It is measured in the kVA rating. Rating of any electrical machine designed by the temperature rise. Got it my point? So temperature rise means losses. What are the losses here in a transformer? One is the iron loss and copper losses. Okay, copper losses depends on the voltage rating of the transformer, whereas iron loss depends on the voltage rating of the transformer, whereas copper loss depends on the current rating of the transformer. But here voltage and current, this is the okay. And what about the power factor? Now we don't know power factor, whether it is connected, okay, whether it is connected to the unity power factor, 0 point power. That means manufacturer doesn't know about the load power factor, whether it is connected to the 0.8, 0.9, 0.9, the 7 like. So that he was considered as highest power factor of the load. So if the load power factor is equal to 1, then what will happen? So this active power so is equal to, okay, here is a V2 I2 power factor is equal to cos theta is equal to 1. So that's why it is called the simply it is a V2 and I2. So it is the apparent power of the transformers. Okay. So now questioning point of view here, always the power rating of the transformer measured in the volt amperes, kilovolt amperes or megavolt amperes, but not in the kilowatts. So from this equation what we conclude, the kVA rating of the transformer directly proportional to the induced EMF, where induced EMF directly proportional to the frequency. So from 1 and 2 equation, kVA rating of the transformer directly proportional to frequency of the transformers. Is that clear now? Any more question? Okay. So next another possibility question from the EMF equation of the transformer. So that is the relation between the B maximum and V1 by F ratio, where V1 is a supplied voltage. Here this the V1 is the supply voltage, okay, and F is a supply frequency of the transformers. Got it? So we know this is the EMF induced in the transformer. E1 is equal to 4.44 the B maximum ANF, okay, N1 values. So AN and N1 are fixed, okay, during the designing. Are getting my point? So this is the, it is a some constant, okay, and here AN is the number of the tons, AN is the net cross sectional area, N1 is the number of the tons. So here size of the transformer cannot be changed during the operation of the transformer, and number of the tons also cannot be changed during the operation of the transformer. So that what we conclude in above equation, okay, in above equation, okay, size of the transformer and number of the tons are fixed, okay, fixed at the time of the designing or manufacturing, okay, manufacturing. So these are treated as treated as constants during operation of the transformers. Got it point? So these are treated as the AN and N1 are fixed at the time of the designing and treated as a constant during operation of the transformers. So all of it clear? So that if you remove all the constant, okay, this constant, this one and here, so that therefore E1 directly proportional to the here B maximum, okay, multiplied by frequency. So from this equation, this is the B maximum directly proportional to E1 and inversely proportional to the frequency. So whereas E1 is the directly proportional to applied voltage, okay, this E1 applied voltage, and this the inversely proportional to the frequency. So therefore you can write, so therefore B maximum the directly proportional to V1 by F ratio. So this condition is valid only during operation of the transformers. Got it point? So during the operation, maximum flux density of the transformer directly proportional to the applied voltage and inversely proportional to frequency of the transformer. Okay, is that clear everyone? Relation between the flux density of the transformer core and V1 by F ratio. Okay, here suppose if you have a question about like this, if the transformer is operated by keeping applied voltage constant, if transformer is operated by keeping applied voltage constant and frequency is reduced less than the rated value, okay, then what will happen? Okay, here, so we know that it is operating condition, so that here during operation, okay, here this is the B maximum directly proportional to V1 by F ratio. So by keeping voltage constant, frequency is reduced below its rated value, maximum flux density of the core increases, right? So increased in the here, in order to increase the B maximum, okay, B maximum, so this is the maximum flux will be increases. So to increase the this B here pi maximum, so magnetizing current, okay, transformer core goes into the deep saturation. Transformer core goes into deep saturation and demands, okay, this is the which demands high magnetizing current. Okay, so already we have discussed this part. Suppose the initially it is a magnetizing current and it is the flux of the transformers phi. So as a magnetizing current increases, what will happen? The flux of the transformer increases linearly up to the saturation. So beyond that it is remains same. So this point is the saturation point, okay, and above the point, okay, this one is the operating point 1, okay, and this point is the operating point 2. So change in the flux here, in order to increase the flux in the saturation region, okay, in saturation region, so more amount of this transformer core goes into the deep saturation. So it is a low saturation and it is a deep saturation. So which the transformer core goes into the deep saturation, so which demands high magnetizing current. Okay, so for example point, suppose it is operated at this point, okay, requirement of the magnetizing current is so at operating point 1, okay, operating point 1, so this current requirement is at 10 amps to create the flux of the 5 Webers. So at operating point to 2, okay, this at this point. So here operating point to 2. So requirement of the magnetizing current is a 100 amps, okay, to create the same amount of the flux. How much change in the flux here? It is almost constant, but requirement of the magnetizing current, I knew 1 and this one is the I knew 2. So now this is equal to 100. So that how much amount of the current? So 90 amps of the current is wasted to create the same amount of the flux. That's why we have to operate the transformer at rated voltage and rated frequency. Any more question do you want to ask? You can ask. Okay. Any more question do you want to ask? You can ask. Otherwise, we'll end up the session today. So these are the place batches taken by the top educators for the electrical and EC branch. So batch number 1 is a target ESE prelims 2021 electrical batch. Another batch for the rank booster batch for the gate 2021 ECE. Another one rank booster batch for the gate 2021 electrical batch B. Okay. And this is the evolve batch for the gate 22. So which was starts on 21st December, which is in English and Hindi. Some of the top educators are taking these place batches. And it is a evolve batch for the gate 22 electrical batch A. So which is in English and Hindi, which was starts on 21st December. So some of the top educators are taking these batches. Okay, it is official Creatrix channel which has 150k plus members. So please join in this group, all of you. And it is Unacademy Gate. This is actually it is Unacademy Gate English. Okay, so English Telegram group. For any PDF class notes, to get the PDF class notes, please join in this group and obtain the all PDF class notes of all teachers. Okay. So these are the different type of channels under the Unacademy: Creatrix Gate Electrical, Unacademy Gate Mechanical, Unacademy Gate Civil, Unacademy Gate English, Unacademy Gate Computer Science, Unacademy Gate Questions, Electrical Junction. Okay, thank you all. Thank you very much. Thank you very much. Okay, we will meet tomorrow with another session. Mostly I will discuss about all the problems based on the EMF equation of the transformer, all possibility questions based on EMF equation of the transformers.